So the Eulerian theorem states that a connected graph, a connected undirected graph, has an Eulerian cycle if and only if all the degrees of all its nodes are even. Okay? For the directed case, the theorem states that a strongly connected graph has an Eulerian cycle if and only if all its nodes are balanced. And by saying balanced, we mean that the in degree of each node is equal to its out degree. Okay? So some part of this theorem, of these two criteria, are actually easy to see. So if we have, for example, let's focus on the directed case. If we have a cycle that visits all the edges of the graph and then ends at the same vertex, at the same node, this actually means that for each node, the number of times we enter this vertex was the same as the number of ways we left this vertex, right? Which means that its in degree must be equal to its out degree. So once again, if there is an Eulerian cycle, then every node in this graph should be balanced. The difficult part, the not so obvious, let me say so, part is the opposite part. So what we need to show is that if all the degrees are balanced, then there is an Eulerian cycle. And this is exactly what we're going to do now. So we will focus on the directed case. So as we've just discussed, if some node is imbalanced, then definitely there is no Eulerian cycle. So what we're going to show now is that if each node is balanced, then there is an Eulerian cycle. And this is exactly the graph shown here on the slide. You can check that for every node here, its in degree is equal to its out degree. For example, for A, we have exactly one incoming edge and exactly one outgoing edge. For the vertex, for the node D, for example, we have two incoming edges. Let me show them. So these are two incoming edges and two outgoing edges. Okay? And the same for the vertex H. We have two incoming edges and two outgoing edges. Okay? So this graph is balanced, and our goal is to construct an Eulerian cycle in it. Okay? What we're going to do is just to go for a walk in this graph. Let's start walking from some node. In this case, let's start walking from A. So we walk from A to B, and then we walk from B to C. So since our graph is balanced, we always, when we enter some node, we always have a possibility to leave this node. This is just because the number of incoming edges to any node is equal to the number of outgoing edges. So what will happen during this walk is that at some point we will get out of edges, right? So at this point we return back to A, and there are no untraversed edges. Yes, let me also mention that of course we are only going to traverse edges that haven't been traversed previously. Okay, so at this point it seems that we are stuck. We returned to the node A. There are no untraversed edges connected to A on one hand, and on the other hand, unfortunately, we haven't yet constructed an Eulerian cycle. So we are just stuck at a vertex A. At the same time, note that at this point we just have a cycle, and also we do remember that our graph is strongly connected. This means that there should be at least one node on our cycle which is somehow connected to the rest of the graph. More precisely, there must be a node on our cycle for which there are outgoing untraversed edges. So in our case, one of such nodes is actually the node C. And also note at the same time that now we have a cycle. And for the cycle there is no beginning and no end, right? So we can start traversing this cycle from any of its nodes. For example, let's assume that we've started to traverse this cycle from the node C. Okay? It is convenient because we can, on one hand, for C there are still some outgoing untraversed edges. At the same time, going from C, we can easily traverse our cycle that was constructed previously. We start from C and we end at C, and then we continue traversing this. Right? This way, by shifting the starting point of our cycle, we make sure to glue some two cycles. I will tell about this more in a minute. So let's continue traversing our graph from the node C. So we go from C to D, we go from D to G, and from G to C. And now we are again stuck at the vertex C. Okay, let's now see what happened. On our first iteration, we started from node A and we constructed some cycle. Okay, this was very roughly, this is how our cycle looked like. Then we realized, so this was vertex A. Then we realized that in our cycle somewhere there is a vertex C for which there are some other untraversed edges. And we found some other cycle. Okay, but then through this node C we can glue these two cycles, right? So because now we can traverse these two cycles starting from the vertex C. So we start from here, we traverse the first cycle this way, and then we traverse this cycle this way. So this way we actually get a larger cycle. Okay, we first constructed some cycle and then we actually extended by gluing some additional cycle. And what we get now is still some cycle that visits some edges, and it is still not an Eulerian because there are still untraversed edges. But now we are going to repeat the same procedure. Now we have a larger cycle, and in this cycle there is a vertex G which still has untraversed edges. So we might assume that our brown cycle here, we started to traverse it from G, then we traverse on all the brown edges, and then we continue exploring the graph. So we go from G to H, and then we get back to G from H. Now we extended our cycle even further, and then we continue from the vertex D, which lies on our brown cycle on one hand. On the other hand, it still has some outgoing untraversed edges. And this way we extend our cycle finally to the Eulerian cycle. Okay, and this basically proves our theorem for the directed case. Okay, now the remaining question is what happens with path instead of cycles. It is actually not so difficult to reduce this criteria to the criteria of the existence of Eulerian cycles. First of all, if we are looking for a path in our graph, then of course not every vertex, not every node in our graph should be balanced, because for the path we have one outgoing edge. Probably we visit this node once more again, but then, so this basically means that for the starting vertex of our path, it has outgoing out degree, which is one more than its incoming degree, and the same is for the end of this path, right? Then, if you would like to get a criteria, first of all, in your graph, if there is an Eulerian path, then these two vertices should be uniquely definable and identifiable, right? So there should be a vertex whose out degree is 1 times larger than its out degree, and vice versa. For the end vertex, it should be a uniquely defined vertex whose in degree is 1 larger than its out degree. And then, but if you add an edge from this ending point to its starting point, then you will get a cycle. And basically then you can use a criteria for cycles. Let me illustrate this on a simple example. So imagine the following graph. So in this case, the in degrees and out degrees are as shown on the slide. So for example, for this vertex, its in degree is equal to 2 and out degree is also equal to 2. This vertex is also balanced and this vertex is balanced. On the other hand, for this vertex we have in degree equal to 1 and out degree equal to 2, which means that this is the only vertex that can be a starting vertex of an Eulerian path. On the other hand, for this vertex, its in degree is equal to 2, but its out degree is equal to 1, which means that it is exactly the vertex that should be the last vertex of an Eulerian path. Okay, now let me try to construct the corresponding Eulerian cycle here. We might, for example, go first here, then here, then here, then here, then here, 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 and here. Okay, so indeed there is an Eulerian path in this graph. But if we would like just to find a simple criteria, then it remains to know that if we add the following edge from the uniquely determined end of the path to the uniquely determined beginning of the path, then what we get is actually an Eulerian cycle in the resulting graph. And for Eulerian cycle, we already have a criteria. So a criteria for a path in directed graph is the following. So there should be a uniquely determined beginning of the path. There should be a uniquely determined end of the path, such that if you add an edge between them, then the graph should become balanced. Okay? Okay, finally, let me conclude this video with mentioning that the method actually that we use to prove that there is an Eulerian path in this graph can be easily transformed into a program or into an algorithm. And indeed, for this problem for finding Eulerian cycles or paths in the graph, there are very efficient algorithms in practice. So even if in your graph there are millions of edges and millions of nodes, it is very easy to find an Eulerian cycle just in blink of an eye.